So today we're going to talk about arc length and the areas of surfaces of revolution, not as opposed to volumes of revolution like we have been. But those are that's literally all we're going to do today. Okay. So arc length. I'm assuming that, of course, you guys know how to find the length of a straight line. I mean, you don't literally take a ruler to it, but you could take a little sort of mathematical abstract ruler to it and just sort of measure how long a particular straight line is. And you might even know how to find the length of a curve if it's a perfect circle. Right? It's just 2 pi times the radius. But for anything in between, like a curve like that, there's not really any tools that you have to determine how long that is. In fact, let me pick up a worse example. Right, so a curve like that, there's no way to tell how long that is. I guess you could probably tell that it's definitely longer than if you just went in a straight line from the starting point to the end point, but that's not a whole lot of information. And it's not like you can really take a ruler and just bend it a bunch until you can use it to measure a curve. So there's going to have to be a different way to do this. And that way is going to be essentially dividing up the curve into a bunch of little segments, or little pieces of curve, and slowly, by adding more and more of these segments, approximating them with a series of straight line segments. Obviously, with a number of segments like this, it's not going to be a perfect approximation, but the more of them that there are, the more of these little straight bits that there are, the better of an approximation you're going to get until, of course, as always happens, you sort of take it to where there's infinitely many bits, and then it's a perfect approximation. But that's basically sort of the basis of how we're going to find arc length. Okay. So we've been using definite integrals to find volume. We can also use them to find arc lengths and areas of surfaces that come from revolving something. You don't actually have to write down this distance formula, but you might remember it. It's the distance between 2 x values squared added to the distance between 2 y values squared, and then square root taken of that. That's just the distance between 2 points in the plane. In xy, and x1, y1, and an x2, y2. Okay. Don't worry about continuous differentiability or a curve being smooth. This is sort of the same thing as what I showed you earlier. Just imagine trying to find the length of a curve from here to here. And then just going to approximate it by a series of line segments that you're going to increase the number of. Okay. Don't worry about this. In fact, we're just going to sort of skip to the actual like formula of this. Okay. But if you want the actual derivation, it's back there. Okay. This is the formula for arc length. This is also the formula for arc length, but it's dy. There's really not that much to it. The whole thing is under a square root. There's a 1 plus, and then whatever f prime is, you square it, and it's 1 plus that underneath the square root. So this is for if the curve is a function of x. And the second one is for if the curve is a function of y. A lot of curves can be written both ways. Yeah, I mean, one of the things that you're sort of meant to learn in calculus too is that there's no fundamental difference between, the variable x and the variable y. It's sort of a weird in-between. You really learn how they're more or less the same in calculus 3, but in calculus 2, you're still working with y as a dependent variable and x as an independent variable a lot of the time. But there's nothing special about y. These integrals are they work the same way. They're in terms of the calculations, they're just as easy as dx integrals. All right. This is not a great example because it just uses a straight line. We'll take an example from the homework. Okay. So the arc length S is equivalent to the integral from, this is dy, so I'm just going to use c and d. The integral from c to d of the square root of 1 plus g prime of y all squared dy. Right, if it were dx, it would simply be f prime of x, and instead of c and d, there'd be a and b, but it's just sort of the same. So this is g of y. It's a function of y. Just like you might call y equal, just like you might say y equals f of x, you can say x equals g of y. But g prime of y, the derivative of this, will simply be, you'll just use the power rule. So, that'll be 3/2 times 1/3 y squared plus 2, now to the 1/2, right? For the power rule for derivatives, you take the power, you put it in front, and then you decrease the power by 1. Then also, because of the chain rule, you're going to multiply this by 2y. Okay, simplifying this a lot, the 3's would cancel out, these 2's will cancel out, and it actually just becomes y times y squared plus 2 to the 1/2. That's g prime of y. So g prime of y squared, as it needs to be squared under the square root, would be, well, that's this squared, which would be y squared times y squared plus 2. Right, the square is going to square the y, and it's also going to square this power of 1/2, which cancels out, and you're just left with the y squared plus 2. So y squared in front of y squared plus 2, which is y to the 4th plus 2y squared. If you were to distribute that, which you probably should. Okay, so S is going to be the integral from y equals 0 to y equals 2, because that's the interval, of the square root of 1 plus 4 y to the 4th plus 2y squared dy. Now, if you rearrange these terms a little, you get y to the 4th plus 2y squared plus 1. Now, you might recognize that this is of the form a squared plus 2ab plus b squared, where a is y squared and b is 1. What this means is that it can be written as y squared plus 1 all squared. Now that it has the 1 incorporated into it, you can write it as 1 squared plus 1 all squared. Or you can simply say, hey, this is y to the 4th. I can try to factor this as, y squared plus a number times y squared plus another number. What are two numbers that multiply to 1 and add up to 2? Well, that's 1 and 1. So I'm going to have y squared plus 1 times y squared plus 1, or just y squared plus 1 all squared. So the square and the square root cancel out. The square root is just a part of this arc length integral. So the integral is really just the integral of y squared plus 1, which is y cubed over 3 plus y evaluated from 0 to 2. So it's 8/3 plus 2 minus 0/3 plus 0. 8/3 plus 2, 2 is 6/3, so that's just 14/3. But it does take integration to be able to do it. just as a reminder, the arc length integral dx is going to be s equals the integral from a to b of the square root of 1 plus f prime of x squared dx. Right, so this is y, but we can also call it f of x. So f prime of x is going to be 1/2 times, well, the derivative of e to the x is e to the x, and the derivative of e to the negative x is e to the negative x times -1 because of the chain rule, so it'll be minus e to the negative x. But that's it, that's the entire derivative. So if you take that f prime and you square it, well, it's like taking two of these and multiplying them together. Or it will be once it's actually, done. Okay. Squaring 1/4 gives you, squaring 1/2 gives you 1/4. And squaring a binomial gives you, okay, just every time a plus b squared, you're going to get a squared, you're going to get 2ab, and you're going to get b squared. So the first thing squared is the first term, the last thing squared is the last term, but there's one term in between where it's like, whatever the two terms are, multiply them together, and you're going to have two of those. That's the 2ab. Okay. So e to the x, if you square it, you're going to have e to the 2x. If you take these and you multiply them together, they have the same base, so you add up the powers. So they actually cancel out, and it just becomes e to the 0 minus e to the 0. And anything to the 0th power is 1, so it's going to be -1, and you're going to have two of those, so it's going to be literally just -2. And then the last thing squared is going to be plus e to the -2x. Okay. So distributing that 1/4 now. 2/4 is 1/2 plus 1/4, give a -2x. Okay. So the bounds of integration are x equals 0 to x equals 2. That's the given interval. So it's going to be 1 plus this whole thing. This is the 1 and the -1/2 combine to create positive 1/2. And I'm going to arrange it in a particular way. I'm going to arrange it in a way that mirrors what the original one looked like. So I'm going to have 1/4 e to the 2x. 1 plus -1/2 is going to be positive 1/2 plus 1/4 e to the -2x. So you might notice that this kind of looks almost identical to this. The only difference is there's a minus here and a plus here. So what we're going to do is we're going to sort of, the same way that this came from squaring this thing, except there's a minus sign in between them, so that's why there's a minus sign right here. There's a plus sign right here, so we can actually condense this down into, and you can do all sorts of things beforehand. You can try factoring out a 1/4. That's perfectly fine. That sort of helps you see what's happening better, but you can actually condense this back down into 1/2. Into being squared, 1/2 times e to the x plus e to the negative x. Right, because with basically the square of 1/2 times e to the x minus e to the negative x, like this, becomes this, 1/4 e to the 2x minus 1/2 plus 1/4 e to the negative 2x. So the only difference is that it's a plus 1/2. The only thing that's going to change is that it's going to be a plus in between the e to the x and the e to the negative x. So then this is just, so the square and the square root cancel out. This is just 1/2 times e to the x plus e to the negative x. Which, if you integrate this, the integral of e to the x is e to the x. The integral of e to the negative x is actually just like the derivative, minus e to the negative x. And this is going to get evaluated from 2 to 0. Right. And so, I mean, you could type it in exact terms of e, but you can also just say you just plug in 2. And in this case, plugging in 0 will still cause it to be 0, but but I'm still going to write it anyways. Okay. All right, so 3.62, say 3.6269. So 3.6269 is the length of that curve from x equals 0 to x equals 2. So for these arc length integrals, because the whole thing is underneath of a square root, and there's not often anything you can do with something that's trapped under a square root, what you're going to be doing pretty much all the time with these arc length integrals is trying to find a clever way to express what's underneath the square root as a square. It happened here, right? We were able to express what was underneath the square root as y squared plus 1 all squared, so that, we cancel out with the square root. It happened here after we incorporated the 1. You wanted to express this, again, as a square underneath the square root so that they would cancel, and it would just become like a regular integral. So that's just how it's going to be with these arc length integrals. Now, the last thing that we're going to talk about is the area of a surface of revolution, which admittedly is a little less important, but yeah. Okay. So if you were to take a curve, not a region, right? If you took a region and you rotated it around an axis in space, you would end up with a volume, which you sort of have been ending up with this whole time. But if you take a curve let's just say that you have a curve like this, and you take it and you rotate it around an axis. Like, let's say you rotate this around the x-axis in space. You're going to end up with a surface of revolution. Now, this looks like a volume, but it's not, because it is hollow. It is not solid and filled in like the volumes of revolution that you've been seeing up to this point. It is literally a surface. It is flat. It has no like thickness. It has no mathematical thickness. Yeah, it's just like this sort of flat sheet, wavy thing. But it has an area to it. Like, it has a surface area. And again, in the interest of time, we're not going to really mess around with the derivation of it, but it does have to do with, like, if you were to approximate this using a bunch of line segments and then take those line segments and rotate them around, what you would end up with is a bunch of sections of cone called frustrums. And frustrums of cones have a volume for their surface area. And the more line segments you break up the curve into, the more frustrums you can break up the resulting surface into, and the closer of an approximation that you can get. Yeah, there's a whole, well, actually, we probably have enough time to actually talk about it. Okay. But yeah, so in the previous arc length integrals, we didn't rotate anything, right? It was literally just measuring like the length of a curve on the plane. if you take a curve on the plane and you rotate it around, you form this sort of, hollow, just two-dimensional. It's two-dimensional in the sense that it has no thickness, but it is sort of a surface existing in space, like a hollowed-out base, or it's just not solid on the inside, right? And all you're worried about is the surface area in this case. If you take a curve and you approximate it by a bunch of line segments, the resulting surface will be approximated by a number of frustrums or frustra. And the formula for the surface area of a frustrum is simply 2 times pi times the average radius of the frustrum times the length, like the sort of length from one end of the frustrum to the other. You don't have to remember that, by the way. That's just, yeah. Right, so this is a section of a curve. If you rotate it around, it forms this hollow. Again, it's just a tube. You could put your arm straight through it. But this sort of shape. And essentially, what happens is you just sort of make a series of hollow rings, and you're gonna. Yeah, I guess we're going to skip to this. That's fine. Okay, so the two real differences between this and the arc length integral are the existence of the 2 pi in the front and the fact that there's a radius function in front of it. But other than that, it's the exact same. It's still the square root of 1 plus, f prime squared, or 1 plus the square root, the square root of 1 plus g prime squared. But it's the 2 pi and the radius that are different. And the first one is for when you're doing an integral dx, where y, and that's going to happen if you can write y as a function of x. And the other one is for when you're doing an integral dy, and you can write that, you can do that whenever you can write x as a function of y. Now, based on how you're rotating it, this radius function may simply be x. And that's going to happen if you have a vertical axis of rotation for these integrals specifically. Or it may be whatever f of x is. Because, essentially f of x is y, but expressed in terms of x. So the radius can be x, the radius can be y, but either way, you're going to want to express it in terms of x. And it can be f of x if it's a horizontal axis of rotation. Okay. Similarly, r of y, it may be simply the variable y. And that's going to be if it's a horizontal axis of rotation. Or it may be g of y if you've got a vertical axis of rotation. Essentially x, except it's going to be expressed in terms of y because it's a dy integral. You know, because x equals g of y. And these are going to go differently from the arc length integrals because there's that extra bit on the outside of the square root. So you no longer have to find a way to express what's under the square root as a square. Because you have this extra little bit on the outside of a square root, that opens up a lot of possible u substitutions. And that's generally how these surface area integrals are going to go as they're going to go as u substitutions because they've got that bit on the outside. Okay. So there's this curve, y equals x cubed, or f of x equals x cubed, from 0 to 1. This is just like a little section of it from 0 to 1, but it gets rotated around the x-axis, so that it forms this hollow sort of lampshade kind of surface, and we're going to try to find the area of that surface. Okay. So capital S is a 2 pi times the integral from x appears to go from 0 to 1. R of x, the radius of this shape, it's a horizontal axis of rotation. So the radius is simply f of x. And f of x is x cubed. So the radius, is y, except we're going to express it in terms of x, so we're actually going to want to say that the radius is x cubed rather than y, even though, y is x cubed. Yeah, so x cubed is our radius function. Now, in terms of f prime, if f of x is x cubed, f prime is 3x squared. And if we take that and we square it, that's 9x to the 4th. Okay. And that's what we're going to place right here. That's f prime of x all squared. That's just sort of the two bits that you need to identify. What is r of x? What is f prime of x squared? But this is actually all ready for a u substitution, because if we let u equals this 1 plus 9x to the 4th, well then du is going to be 36x cubed dx. And we have that, and we have the x cubed that we need. It's literally right there, right outside the square root. Okay. Okay, so to do that, to sort of accomplish that, you could divide by 36 on both sides of this and then get some sort of deal, but I'm just going to shove a 36 into here. And make sure to divide by 36 on the outside. Is how I'm going to do it. You can do it however you like. Okay. But this is u. And actually, what would probably be better is so this is u. And this is du. Okay, so that this is going to be the square root of u du. And instead of x going from 0 to 1, right now technically u goes from 1 to 10. And you can do that just by plugging in your bounds for x, 0, and 1 into the substitution u equals 1 plus 9x to the fourth. If you plug in 1, or sorry, if you plug in 0, you get 1. And if you plug in 1, you get 10. This is u to the 1/2 du. So integrating that should give you u to the 3/2. So 2 pi over 36 times u to the 3/2 divided by 3/2, or 2/3 u to the 3/2. Evaluated from u equals 1 to u equals 10. Because if you take this substitution, so the original bounds were for x, right? And x went from 0 to 1. While it's in terms of u, technically, like we can't really speak about it, the bounds in terms of x anymore, because we've temporarily changed it into terms of u. So if you plug in x equals 0 into this substitution, you're going to get u equals 1. And if you plug in x equals 1, you know, your upper bound, into the substitution, that's going to be 1 plus 9 times 1, or 10. So while x goes from 0 to 1, u goes from 1 to 10. Now you're entirely free, after you do this integration, to switch it back into terms of x and use x equals 0 and x equals 1 again. But ultimately, you will just be doing the same thing as, you know, plugging in 10 and finding whatever 10 to the 3/2 is, and like you'll be doing the same numerical things either way. So this could probably be simplified. I mean 1/18, right? But also 18 over 2 is 1 over 9, so 1 over 27. I'll say it's 1 over 27. Okay, so plugging in 10 and plugging in 1 should give you, well, it should just be the difference between 10 to the 3/2 minus 1 to the 3/2, which is 1. And if you like, you actually can, you can do this. You can do switch it back in terms of x, 1 plus 9x to the 4th to the 3 halves, evaluated from x equals 0 to x equals 1. Either way, you're going to end up with 10 to the 3 halves minus 1 to the 3 halves, or just 10 to the 3 halves minus 1. It only looks like a long interval because I'm trying to skip as few steps as possible, but like at this point, once it's a u substitution, it literally just, the only integration you have to do is integrating the square root of u, or like u to the 1/2. And that just ends up being, this sort of power rule, or sort of power rule business. Once you identify once you set up the integral. So that's approximately approximately 1.134, which is just to say that in terms of square units of area, it's a little more than 1 square unit of area, like in area. This sort of lampshade sort of sheet thing. Oh, right. Also, there's a pi, so I completely forgot about that. Somewhere here, exactly here. So there's a pi here, and a pi here. So that actually means it's around 3.5 square units of area around, which is probably a more realistic answer anyways. Okay, so just to recap, I know sort of rushed through it, but so there are 2 new kinds of integral. Not really new kinds, but like 2 new applications for an integral, which I'll give you the formula for when the time comes. One of them is arc length, which lets you determine the length of a curvy piece of function. Something doesn't have to be a straight line for you to measure it anymore. And that's this integral. Like the whole thing is a square root. And because the whole thing is a square root, all you're going to ever try to do when you're dealing with arc length is try to get what's under the square root to be expressed as a square, so that you can cancel out the square root. Because it's not really going to be doable otherwise. So you want to be able to express what's under the square root as a square, like here, so that you can cancel it out, or here, so that, again, you can cancel it out with the square root that's over the whole thing. And that's for arc length. For surfaces of revolution, you're not going to have to do that because there is this extra bit on the outside. it might simply be the variable you're using, or it might be the curve that you're actually talking about based on, and that's going to be based on whether it's a vertical axis of rotation or a horizontal axis of rotation. But you're going to have a little extra bit on the outside that's going to allow you to do a U substitution where it would otherwise be impossible. Because you have that little bit, you don't have to do the same thing with these integrals, try to get what's under the square root to be a square. You can just sort of be ready to be doing a U substitution in order to deal with these integrals. And, just like this one did. Yeah. And that's going to be possible because you have this part that's going to be, the part that's going to be your U is likely going to be the entire underneath the integral. And then your du is going to incorporate that bit that's on the outside of the square root.